This is Babitha, working as Assistant Professor in the Department of ECE at Institute of Aeronautical Engineering. In this session, I am going to discuss about hybrid pi model of common emitter transistor. So before going to that, while coming to the contents, here I'll just revise the transistor small signal analysis that is required to do the hybrid pi model. And what is the approximate small signal analysis? And then we'll move with the transistor hybrid pi model. So here, how we can able to get the transistor small signal analysis. For that, we have to consider the transistor amplifier circuit in any configuration. In this case, I am considering here it as common emitter configuration. So for this amplifier, to make it a small signal analysis, we have to short all DC sources which are present in the circuit, as well as we have to short all the capacitors, all the coupling capacitors, as well as input capacitors and bypass capacitors which are present in the circuit should be short circuited. And we need to represent the transistor in its hybrid model. Okay, we need to represent the circuit in its hybrid model. So to represent the transistor in its hybrid model, we have to convert the transistor in its H parameter model. So in the case of transistor, we are having two input parameters, that is input voltage and input current, and two output parameters, those are output voltage and output current. Though here I am considering the common emitter configuration, in this particular case, input parameters are VB, base to emitter voltage, and the input current is base current IB. And similarly, the output parameters are collector to emitter voltage VCE and the collector current IC. So these are the input as well as output parameters of the common emitter amplifier. To represent this common emitter transistor in terms of hybrid model, I am representing these four parameters in the form of dependent and independent parameters. So among these four parameters, two parameters, that is VBE as well as the IC, I am taking here it as dependent parameters. These are the functions of IB and VCE, and this is also function of IB and VCE. So here VBE and IC are the dependent parameters, IB and VC are the independent parameters. If we represent in this way, we can able to form the H parameters required to draw the hybrid equivalent circuit. So these equations I am writing in this way. This I am taking here it as 1 and 2. So from this 1 and 2, I am writing here it as the variation of VBE. I am writing here it as the variation of VBE divided by variation of IB into variation of IB. If we get cancel these two means, again we will get it as dVBE only. And similarly plus dVBE divided by dVCE into dVC. You can take it as dou. Why? Because we are representing here it as variation. So this one I am taking it as my third equation. And similarly second equation also I can write it as dou IC is equal to dou IC by dou IB into dou IB plus dou IC by dou VCE into dou VC. So this is my fourth equation. So I can represent these variations as the H parameters here. So this is the first H parameter, H11, or we can call it as HIE. And this is H12. That is nothing but we can call it as HRE. And this parameter we can call it as H21, that is nothing but HFE. And the last parameter we can call it as H22, that is nothing but HOE. So now we will derive all these four parameters. So the H11 and HIE is nothing but the variation of dou VBE by dou I. So before moving to this, I can replace this third equation with VBE equal to HIE IB plus HRE BC. I'm taking it as fifth equation. And this fourth equation, I can write it as IC equal to HFE into IB plus HOE into BC. So this is my sixth equation. So from the fifth and sixth equations, we can able to find all the H parameters. So the first H parameter HIE from the fifth equation, I can write it as, to find this particular HIE parameter, VCE should be short circuited. So once VCE is short circuited means HIE equal to dou VBE by dou IB when VCE is equal to 0. So though these two parameters are related to the input port parameters of the transistor, that is input voltage and input current. So that's why we are calling it as input impedance. So the parameter HIE is called as input impedance. And similarly, the second parameter, that is H12, that is nothing but HRE. So to find this particular HRE value, we have to make IB as 0. We have to open circuited the input current which is flowing in the transistor. So once we open the input terminals, we will get it as dou VBE by dou VC when IB is equal to 0. So here, generally the output voltage by input voltage indicating the voltage gain, but here we are getting the input voltage divided by output voltage. It is in reverse form. So that's why we are calling it as reverse voltage gain. Okay. And similarly, to find the remaining parameters, I am considering the sixth equation. In the sixth equation, when the VC is equal to 0, the output terminals are short circuited. When the output terminals are short circuited, I can write my H21 or HFE is equal to dou IC by dou IB when VC is equal to 0. So it is the ratio of output current to input current. So we can write it as forward current gain. This is when the output is short circuited. And similarly, we can find the last parameter, that is H22. And also we can call it as output admittance. HOE is nothing but the variation of the collector current to the variation of the collector to emitter voltage when base current is open. So in this case, we can call it as, generally voltage divided by current, we can call it as the resistance. So that's why first parameter we have written it as input impedance. But here we have the output current by output voltage. So it is reverse of the resistance. So that one we are calling it as output admittance. So these are the 4 H parameters. So by using these 4 H parameters, we can able to draw the hybrid equivalent circuit of the transistor or small signal equivalent circuit of the transistor. So for that, I am considering the 3 terminals of the transistor here. That is base, collector and emitter. Why I am taking emitter down means we are considering here it as the common emitter amplifier. So that's why base terminal is common or grounded between base and collector terminals. So this is the input side and this is the output side of the transistor. So here, if we observe, Among the 4 parameters, this input impedance as well as reverse voltage gain, in these 2 cases we are having the input parameters or input port related parameters. So that's why these 2 parameters we are going to represent in the input port of the transistor. So HI is nothing but the voltage to the current ratio, that is nothing but resistance. So that resistance I am representing with HIE. Okay. And next parameter is reverse voltage gain. So in order to represent voltage gain, we don't have any symbols. So that's why we are converting this gain into voltage source. So to convert it into voltage source, I am making it as VBE by VCE multiplied with VC. So in this, VBE by VCE is nothing but our HRE multiplied with output voltage VC. So now this voltage gain in terms of voltage source we represented. So this one I am including in the circuit. This value is HRE into VC. And similarly, in the output side, we are having 2 more parameters, that is forward current gain and output admittance. Again, to represent the current gain, we don't have any symbols. So that's why I'm converting this current gain into the current source by multiplying it with the input current. So here IC by IB is nothing but our HFE multiplied with base current IB. So this one I am including here. This value is HFE into IB. And the last parameter is output admittance. Admittance is the reciprocal of the resistance. So that's why this admittance I am representing with the resistance, and I am writing it as 1 by HOE. So input side, the input current IB and the input voltage VB is present, and the output side, the collector current IC and the output voltage VC is present in the circuit. So this is the transistor small signal model by using hybrid parameters. So this is the circuit we can utilize for the analysis of the amplifier circuit. But in some cases, if we are using the multi-stage amplifiers and different coupling amplifiers, in that case, this particular analysis is not useful. Why? Because in order to find these many parameters, it will take so much time and it will be lengthy process and it will be complex. So in order to overcome all these problems, we are moving for the approximate small signal model. So in the case of approximate small signal model, generally why we are moving for this means the H parameters are varying for different type of transistors. If we take 2 similar transistors also, the H parameters will be different here. So by using the approximations, and we can able to simplify the amplifier parameters, that is current gain, voltage gain, input impedance, output impedance, as well as power gain. All these parameters, by using approximations, we can able to find. So the behavior of the transistor circuit we can obtain by using the simplified hybrid model here. So the H parameter equivalent circuit of the transistor in CE configuration we have already drawn here. In the previous slide it is there. So in this particular case, I am taking that circuit again here for reference. This is the base, collector and emitter terminals. We are having the resistance, and here it is HRE into VCE, and here we have HFE into IB and the output admittance. So this is the circuit for the exact model. So here 1 by HOE parameter is in parallel with the load resistance RA, if we observe in the equivalent circuit. So here these Parallel combination of these two unequal resistances will give the lower value as the output. So if we compare these two, RL will be low. So that's why 1 by HOE is far greater than RL value. So if we assume this particular condition, we will get it as HOE into RL is less than 1. So once this value is very less, means we can able to neglect the 1 by HOE term in the output side. So we can able to neglect this 1 by HOE term. So once this 1 by HOE term is neglecting in the output side, what is the effect in the collector current or output current? So the collector current is equal to HFE into IB here. Okay. And what about this HREVC? What is the effect in this HREVC also? We have to see. So the magnitude of the voltage generated, that is nothing but output voltage of the circuit, is HREVC. And what is the value of VC here? The current through the collector terminal IC as well as load resistance RA. So VC equal to IC into RA. And again IC value from the circuit is HFE into IB. So after substituting that, we will get it as HRE HFE IB into RA. So in this case, if this particular HRE HFE value is very less, that is approximately equal to 0.01, so this particular voltage we can neglect. Why? Because this voltage drop is very less compared to the voltage drop existing across the HIE resistance. So that's why, because of that reason, we are neglecting HRE as well as HOE in the exact analysis. So after omitting this HRE and HOE in the exact model, we will get the approximate model as only in the input side we are having HIE and in the output side we are having HFE into IB. Right? The load resistance RA. So this is the approximate model for the hybrid equivalent circuit. So next thing is we have to see the transistor at high frequency so that we can able to draw the high frequency pi model of the transistor. So here generally low frequency signal is nothing but if we take the frequency range from 10 to kilohertz range, 10 to some 100 kilohertz range, so that we can say it as the small signal. So whatever the small signal model or hybrid model we discussed till now, that is applicable for the low frequency signals till 100 kilohertz. But if the frequency of the signal is increasing, means the capacitance of that circuit will also increases. Why? Because the reactance of the capacitor is always inversely proportional to the frequency. That is Xc equal to 1 by 2 pi Fc. Here as frequency is increasing, the reactance of the capacitor is decreasing, so that the capacitance value is increasing. So once that capacitance value is increasing, means the effect of that capacitor is we need to include in the analysis of the circuit. So in that case, this small signal model, whatever we discussed till now, is not applicable. Why? Because in that case, we removed all the capacitors and we removed all DC sources. But in the case of high frequencies, we need to include the capacitors. And also one more reason here it is, the H parameters itself are not constant for all the similar type of transistors. And those are not same for all high frequencies. So that's why it is necessary to analyze the transistor at all frequencies. At each and every frequency, we have to analyze the transistor. But it is very impracticable and it is very complex also. So that's why, in order to compromise all these reasons and to get the analysis of the transistor at high frequency, we are going for the hybrid pi model in order to analyze the transistor at high frequency signals. So this high frequency pi model is also called as Giacoletto model. So this particular transistor high frequency hybrid pi model will provide the accuracy as well as simplicity to do the high frequency analysis of the transistor. That is nothing but the analysis will be simple and it will give the parameters in simple way without any complex derivations. So that's why we are moving for the transistor at high frequency. So before going to the transistor at high frequency or hybrid pi model, again I am considering the H parameter model, whatever we derived till now. So this is the hybrid equivalent circuit of common emitter transistor, or H parameter model for the common emitter transistor. So this is in the case of low frequency signals or small signal analysis. But to do the analysis in the high frequency, I have mentioned that the capacitances should be included. So that's why in the small signal H parameter model itself, we are including all the capacitors which are present in the high frequency of the circuit. So for that, when we are going for the hybrid pi model or high frequency model, one extra terminal is added to the transistor, that is B dash. Generally in the transistor we are having only 3 terminals, those are emitter, base and collector terminals. But at high frequency, when we are designing the circuit, one more extra terminal is added, that is B dash, that is base spread resistance or base spread terminal. B dash is extra adding in the circuit. So here in this case we are having base, collector and emitter terminals. But here in the high frequency model we are having base, collector, emitter, along with this one more terminal B dash is included here. And we are also including all the spread resistances in all the terminals. Here RB B dash is the base spread resistor. RB B dash is the base spread resistor that is existing between the base terminal B and B dash. And RB dash C is the resistance between the B dash and collector terminal. And RB dash E is the resistance existing between the B dash terminal and emitter terminal. So because of including this extra terminal, it is providing the spread resistances to all the remaining 3 terminals in the circuit. So that's why we are getting 3 extra resistances in the hybrid equivalent circuit between B dash and B, between B dash and C, and between B dash and E. And one more resistor between the output terminals, that is collector to emitter terminal, that is RCE also included. So total 4 resistors are included. And capacitors, the capacitor between the B dash and collector and the capacitor between the B dash and emitter terminals. Here 2 capacitors are also included in the hybrid pi model of the common emitter transistor. So now we will see this each and every resistance values and how they are affecting the analysis of the circuit, and also each and every capacitors. So I have already mentioned the extra terminal B dash is added to the circuit, but it is not visible to us. It is internally present in the circuit. So and this resistance, because of including this particular resistance, because of including this particular terminal, between all the terminals the resistance is existing here. So this B dash is nothing but the internal base terminal, so that is not accessible to us. So this particular B dash is separated by the physical base terminal B by a resistance denoted by RB B dash that we can observe in the circuit. So with RBB dash resistance, we can able to differentiate the base terminal and base spread terminal. So now we'll discuss about the first resistance, that is RBB dash. So what is mean by this RBB dash? Here I highlighted only RBB dash. Why? Because we are going to discuss about now RBB dash. Here RBB dash is the base spreading resistance. So this is the equivalent resistance between the base terminal as well as base spread terminal B dash. So between B and B dash, we can able to this particular resistor. And the value of this particular resistance is depends upon the how much total current which is flowing in the input resistance. How much input current which is flowing in the input resistance. And generally this resistance RBB dash is negligible. Why? Because at low frequencies this value is less than 100 ohms. It is very less, so that we can able to neglect at low frequencies. But at high frequencies we need to include this RBB dash value. And the next resistance value is RB dash E. So RB dash is the resistance between the base spread terminal as well as emitter terminal. So this input resistance RB dash is the resistance between the base terminal as well as the emitter terminal, and it is indicated as R pi of or else RB dash E. Why? Because it is existing between the base spread terminal as well as emitter terminal, so that we can write it as RB dash E. And this particular model we are calling it as the hybrid pi model, so that's why we can also write it as R pi. So this input resistance is approximately equal to the H parameter input impedance, that is HIE. So RB dash is almost equal to the HIE. So if we short the output terminals of this circuit, that is nothing but collector emitter terminals, in that case the base collector junction is reverse biased, that is the output junction is reverse biased. So once the output junction is reverse biased, it means its resistance value is very high, and that resistance value is far greater than the forward biased base emitter resistor. So that's why RB dash C value is very high compared to the RB dash E value. Why? Because in the case of transistor, input junction is always forward biased, output junction is always reverse biased in order to operate in the active region. So this RB dash E present in the input side, RB dash C present in the output side. So since output junction is reverse biased, so that's why RB dash C value is very high compared to the RB dash E. So to find the expression for this R pi value is equal to, we have mentioned here it as input impedance HIE. So that HIE, how we can calculate from the circuit is this RBB dash, the total input impedance RBB dash plus the parallel combination of RB dash E and RB dash C. So that is RB dash plus RB dash E parallel with RB dash C. And here we have already mentioned RB dash C value is greater than RB dash E. So if we take two unequal parallel combination of resistances, we will get the output as lower resistance value. So that's why RB dash E we will get from this parallel combination. So the total R pi value is approximated as RBB dash plus RB dash E. This is the input resistance RB dash E is existing between the base spread terminal and emitter terminal. And the next one is capacitor C, which is existing between the base spread terminal and emitter terminal. And we can also call it as output capacitance. We can represent here it as CCE or C. So this capacitance is between the collector and emitter terminal. So this capacitance value is extremely small, so that we can able to ignore in the case of small frequencies. Why? Because input capacitance is very high compared to this output capacitance. Again, because of the same reason. The input junction is forward biased. So once the input junction is forward biased means the depletion region width is very less. Once the depletion region width is very less means the input capacitance value will be very high. And similarly, if you take the output side is reverse biased. So once it is reverse biased, it means the depletion region width is increasing. So once the depletion region width is increasing means definitely the capacitance value is decreasing. So here the output capacitance value is very less compared to the input capacitance value. So that's why we are neglecting this output capacitance value C. And the next parameter is RB-C, the base spread resistance between the base terminal as well as collector terminal. So this resistance we can also call it as feedback resistance. So it will affect the collector voltage on the base current. So because of presence of this resistance, there is a change in the collector voltage. Once the collector voltage is changing means the base current will also change. So if we looking in the circuit, RB-C is very less and that value is beta naught into R naught. And beta naught is nothing but the value of the beta at very low frequencies. This beta is nothing but the DC gain. So this DC gain at low frequencies, this value is very less. And why this value is very less means when the output junction is reverse biased. When the output junction is reverse biased means the gain value is decreasing here. So that's why this value we are taking here it as less. So this feedback resistance is related to the reverse voltage gain in the H parameter model, that is HRE. So HRE is the reverse voltage gain, that is input voltage by output voltage. So in the case of CE transistor, input voltage is VBE and the output voltage is VC. So if we take VBE by VCE from this circuit, we will get it as RB-E divided by RB-E plus RB-C. And again, this RB-E value is very high compared to the RB-C. So we are neglecting here RB-E. We will get it as RB-E divided by RB-C. And the next resistor is RCE, collector to emitter resistor. So it is existing between the collector and emitter terminals. And the last one is GM, VBE-R, this capacitance CC, collector to base capacitance CB-CR, we can also call it as CC. So this is the capacitance existing between the collector base junction and its value is small, between the range of 0.5 to 5 picofarads. And the value of this capacitance depends upon the width of the junction of depletion region. And generally, we can consider it as constant over a specific region of operation. Why we are making it as constant means if we make it as constant only we can able to get the maximum capacitance. If it is varying with the junction voltages means the depletion region width will also changes, so that the capacitance value will also changes. So that's why when we are operating with certain frequencies, we will make it as some constant value and we'll do the analysis. So this capacitance is indicated in the spec sheets as COB, but may also referred as C micro. We can represent it as C micro also. So in the case of hybrid pi common-emitter transistor model, these are the parameters we discussed now, that is diffusion capacitance between base spread terminal and emitter, that is CE and CBE, and the CPC CB-C capacitance existing between the base spread terminal and collector, and ohmic base spreading resistance is RB-B-, and resistance between the base spread terminal and emitter is RB-E, and the resistance between the reverse biased base spread as well as collector terminals is RB dash C, and the transistor conductance is GM, and the output resistance between the collector and emitter terminals is RC. So these all are the parameters we discussed, and we need to find all these parameters from the hybrid pi model. So to find that values, we require these H parameter values, hybrid pi parameter values at room temperature. When we consider at room temperature, the collector current, we will get it as 1.3 milliamps. So when the collector current is at 1.3 milliamps, these are the values of all these parameters. We will get these particular values at collector current is equal to 1.3 milliamperes, and in that case we have to maintain room temperature. And next we need to find the parameters of all conductances as well as capacitances existing in the hybrid pi model. So in the conductances, we are going to calculate transistor conductance GM and the input conductance between the input terminals GB-E, and the feedback conductance between the collector to base spread resistance and the base spread resistance RBB- and the output conductance between the collector to emitter terminal. So the first parameter we are going to calculate here, it is transistor transconductance GM. That is output current by output voltage. So to calculate that, we are taking the amplifier circuit, common emitter amplifier circuit with B dash terminal included, because it is at high frequency. Once B dash is included in the circuit, means along with that RBB dash is also included in the circuit. So here transconductance is the ratio of collector current to the input voltage VB, that is the rate of change of collector current to the rate of change of input voltage, that is G. So to find this value, we require the collector current as well as input voltage PV-E. So generally the collector current equation from the operation of the transistor is IC0 minus alpha IE. IC0 is the leakage current or reverse saturation current when the transistor in the reverse bias condition, and alpha naught IE is in the forward bias condition current. So while calculating the total current, we have to take the sum of both the reverse saturation current as well as the forward biased current. So here alpha naught is nothing but the current amplification factor in the amplifier circuit. So from this we can write dou IC equal to minus alpha naught I. Why we are writing in this way means the value of IC naught is very less compared to the IE here. IC naught is the reverse saturation current when the reverse bias condition. Generally we will not able to use this particular reverse bias current in order to run any applications. So that's why we are neglecting that. After neglecting that reverse current, IC equal to minus alpha naught I. So from this we can write GM from the first and third equations. In the first equation, if you substitute the IC dou IC value, we will get it as GM equal to minus alpha naught dou IE by dou VB-E. So for example, if we take it as the PNP transistor, in the PNP transistor, VB-E is nothing but emitter voltage V. So we can write it as GM equal to alpha naught dou IE by dou VB-E. And if the emitter resistance is RE, so that emitter resistance is existing between the emitter voltage and emitter current. So that's why dou VE by dou I. So then GM equal to alpha divided by RE. Why? Because here we have IE by VB, but here we have VE by IE. It is in reverse form. So that's why we included in the denominator alpha naught by RE. And next we need to find the RE value to find the overall transconductance. So the dynamic resistance of the forward biased diode is RE equal to VT by IE, that is voltage equivalent of the temperature divided by emitter current. So how we can calculate this voltage equivalent of the temperature? That is by using kT by Q, that is Boltzmann constant. K is Boltzmann constant into temperature T divided by charge of the electron Q. So from this we can write Gm equal to IE alpha naught IE by Vt. Why? Because we are substituting the value of Re here. Re is Vt by I. So after substituting that, we are getting it as alpha naught IE by Vt. And again, IE is nothing but alpha IE is nothing but IC naught minus IC divided by Vt. And again in the PNP transistor, the collector current value is negative. So for NPN transistor, IC is positive. So that's why we represented in the determinant. With VE equal to VB dash E, we will get it as GM equal to IC minus IC naught by VT. So for any type of transistor, GM should be positive here. And here IC value is very high compared to IC naught. So that's why we are approximating the transconductance GM as IC by VT. So the output current by the voltage equivalent temperature VT. And if you substitute the value of Vt, that is kT by Q, Gm equal to IC Q by kT. And at room temperature, that is at 300 degrees Kelvin, the values of Q is 1.6 into 10 power minus 19, that is charge of the electron. And the Boltzmann constant value is K equal to 1.38 into 10 power minus 23. And the temperature is 300 kelvins. After substituting all these values, we will get it as Gm equal to IC by 26. And these values are very high compared to the transconductance of the FET here. So if we compare the transconductance in both the BJT and FET, in the BJT we will get more transconductance. And the second parameter is input conductance GB dash E. So from the RB dash E we can able to find the GB dash E. Why? Because the reciprocal of RB dash E will give the GB dash E. So for that again we are taking the hybrid pi model at low frequencies. At low frequencies some parameters are neglected, some capacitors are also neglected. So after removing all that capacitors we will get it as the hybrid pi model equivalent circuit. And along with that, I am also considering the hybrid equivalent circuit at low frequencies. This one we discussed in the second slide. So while determining the input circuit parameters, the output terminal should be short circuited. So that's why the output voltage VC is 0. And while determining the output parameters, the input terminal should be open circuited. So once the input terminals are open circuited means IB equal to 0. So this is here. Here IB equal to 0 while calculating the output parameters and VC equal to 0 while calculating the input parameters. And I'm assuming here it as output is short circuited, that is nothing but VC equal to 0. So once VC equal to 0 here means we will get it as IC equal to HFE IB. So this is from the low frequency model. Okay, this particular value is from the low frequency model, IC equal to HFE IB. And similarly from the hybrid pi model, how much value we are getting? So from the hybrid pi model, VB dash E is nothing but the input voltage is nothing but the input current and input resistance RB dash E into IB. And here our assumption is output terminals are short circuited, so that's why VC is equal to 0. So once the VC is equal to 0, from the hybrid pi model, the collector current IC, we will get it as GM into VB dash E. And VB dash E value is this much. If you substitute here, we will get in this way. And from this, I am taking IB to the left side. IC by IB equal to GM RB dash E. And here IC by IB is nothing but the forward current gain, that is HFE is equal to GM RB dash E. And from this, if you write the RB dash E value, that is equal to HFE by transconductance GM. So RB dash E is HFE by GM. GB dash E is reciprocal of this RB dash E. So that's why GM by HFE. And if you substitute the value of GM here, that is IC by BT. So IC divided by HFE BT is the input conductance GB dash E. That is nothing but to calculate any parameter in the pi model, we have to take the small signal hybrid equivalent model as well as high frequency equivalent model. From both the cases, we need to find the parameter and we have to equate the two parameters to find the parameters in the hybrid pi model. And next parameter is the feedback conductance, that is GB dash C. From the RB dash C, we can able to find the feedback conductance GB dash C. For that, again we are considering the hybrid pi model at low frequencies and also H parameter model at low frequency. So here actually it is a feedback conductance. To find this, input terminal should be open circuited. So once input terminals are open means base current is 0. So from the H parameter model, if the base current is 0, we will get it as input voltage VB dash is equal to reverse voltage gain HRE into output voltage VC. But from the output part of the hybrid pi model, we will get it as I1 by VCE divided by total resistances RB dash E plus RB dash C. So VB dash E we can write it as I1 into RB dash E and substitute the value of I1 here. So from the first and two equations, we can write it as HR VCE is equal to VCE RB dash divided by RB dash E plus RB dash C. So here VCE will get cancelled, and if you cross multiply this one, we will get it as HRE into RB dash E plus RB dash C is equal to RB dash E. And from this, if we write RB dash C, and if we send this particular term to right side, we will get it as RB dash E minus HRE into RB dash E divided by HRE. And if you take RB dash E common, you will get this much. And here, this HRE value is very less compared to the one. So we can neglect this HRE. So once if you neglect this HRE, RB dash C value is RB dash E divided by HRE. So GB dash C is the reciprocal of this RB dash C. So that is HRE by RB dash E. And again, this RB dash E we can represent with GB dash E. Why? Because GB dash E equal to 1 by RB dash E. And GB dash E value already we have calculated, that is IC by VT. So after substituting all the values, the feedback conductance GB dash C is HRE into IC by HFE into VT. And the next parameter is base spreading resistance RB B dash, between base and base spread resistance. So the hybrid pi model at low frequency I am considering here, as well as the H parameter model at low frequency also I am considering here. So we need to find this parameter in both the models. So in the case of H parameter model, the output is short circuited, means the output voltage is 0. So in the H parameter model, once the output terminals are short circuited, means the input impedance is equal to the hybrid equivalent input impedance, RA equal to HIE, since VC equal to 0. And from the hybrid pi model, RA is nothing but the combination of this resistor and this resistor. So RBB dash plus parallel combination of these two resistances. That is RBB dash plus RB dash E parallel with RB dash C. And again RB dash C value is very high, so that we will get it as RB dash E. Why? Because both are in parallel. So from this, two equations, we can write HIE equal to RBB dash plus RB dash E. And from this RBB dash equal to HIE minus RB dash E. So RBB dash equal to HIE minus RB dash E value, just now we have calculated, that is HFE VT by IC. So this is the base spread resistance value. And the next parameter is output conductance, GCE. From the RCE resistance, we can able to find the GCE. So to find this parameter, again we are considering the hybrid pi model as well as H parameter model at low frequencies. So to find the transconductance, output transconductance, input terminal should be open circuited. So that's why IB equal to 0. So from the H parameter model, when the input terminals are open circuited, 1 by HOE equal to VCE by IC we will get. Generally HOE is nothing but IC by VC. This one we discussed already. So HOE equal to IC by VC when IB equal to 0. This one we are taking it as first equation from the H parameter model. And similarly from the hybrid pi model, if we apply the KCL, the collector current we will get it as VCE by RCE plus GMBB dash plus current through the input terminal IB. And here we can substitute the values of BB dash E and I1 we calculated already. After substituting the two values, we'll get this much. And again, after simplification, we'll get this second equation. So from the first and second equations, the output conductance GCE, we can get it as 1 by RCE plus 1 by HFE divided by RB dash E plus RB dash C. But here we require GCE value. So we have to take it as inverse of this one. So that's why GCE we will get it as HOE minus HFE into GB dash C. Here we are neglecting the one in this. Why? Because forward current gain is very high compared to the 1. And also the reverse biased resistance RB dash C is also very high compared to the input resistance RB dash E. So that's why we are neglecting this one as well as this one here. So these are the parameters we have calculated from the hybrid pi model. These are the values till now we have calculated from the hybrid pi parameter model. So in this session, we discussed how to draw the hybrid pi model of the transistor at high frequencies and how to calculate all the resistances as well as capacitances which are present in the hybrid pi model at high frequencies. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.